On a clear, calm, cloudless day, perfect flying weather by any normal measure, more than 40 flights were grounded at a major airport for one reason. It was too hot, not too windy, not too foggy, too hot. And as the planet warms, this is happening at more airports, more often, every single year. But this isn't airlines being overly cautious. So what is it about heat that a 400-ton jet, engineered to cross oceans, simply cannot overpower? The answer involves air that quietly disappears, an engine that loses its strength, a temperature limit no pilot is allowed to cross, and a climate that is steadily pushing more runways past the line. To understand why a heavy aircraft cannot muscle its way off the ground when the temperature climbs, we must look at the invisible medium that supports it. A wing does not float. It relies on physical contact. As it moves forward, it must physically push against air molecules to generate a pressure differential, the lift that overcomes gravity. On a standard cool day at sea level, at a temperature of 15 degrees Celsius, a single cubic meter of dry air weighs about 1.225 kilograms. This dense packing of molecules provides a solid fluid medium for the wings. But when the thermometer rises to 40 degrees Celsius, the laws of thermodynamics take over. The air expands, the molecules spread out, and that same cubic meter of air now weighs only 1.058 kilograms. This represents a density drop of roughly 13%. For a runner, this change is barely felt as a slightly thinner breath of air. For a wing, however, the difference is catastrophic. 13% fewer molecules are flowing over the aerodynamic surfaces every second. This means that at the exact same forward speed, the aircraft generates 13% less lift. Physics does not negotiate. To make up for this invisible loss, the aircraft must either travel significantly faster down the runway to gather the necessary number of molecules, or it must weigh less. The wing simply does not have enough substance to push against. A 10 degrees Celsius rise in temperature reduces AR density, and therefore lift, by about 5%. When the air warms, the wing loses its physical grip on the sky. To compensate for this invisible shortfall, the aircraft must generate more aerodynamic force by running faster. The mathematics of flight dictate a direct reality. To make up for a drop in air density, a jet cannot simply perform its standard takeoff. It must accelerate to a higher true airspeed before the wings can support its weight. For a typical commercial passenger jet, this means reaching a liftoff speed several knots faster than would be required on a cool morning. But speed is not free. It requires distance. To reach these higher speeds, the aircraft must roll further down the concrete. A longer takeoff roll directly translates to a demand for more runway. This creates the first operational barrier. The aircraft requires more runway at the exact moment its aerodynamics are at their weakest. The physics of lift demand a longer runway, because the aircraft must travel faster to experience the same number of air molecules passing over its wings. If thinner air over the wings were the only obstacle, the solution would be straightforward. Perhaps the aircraft would simply accelerate harder, using the extra concrete to force its way into the sky. But a wing does not fly on its own. While the loss of wing lift is a matter of basic aerodynamics, the second reason extreme heat cripples aircraft performance surprises almost everyone who learns about it. A jet engine is at its core an air-breathing machine. It requires a constant stream of heavy, dense air to mix with fuel and generate the thrust that pushes the aircraft forward. When the temperature rises, the air molecules drift apart, meaning a smaller mass of air enters the intake every second. Less air mass entering the engine directly results in less thrust, leaving the tailpipe. Why does this matter? This drop in engine performance creates a challenging intersection of physics. At the exact moment the wings require a higher speed to climb, the engines have less power to get them there. To calculate this penalty, aviation relies on a concept known as density altitude. This metric translates local heat and atmospheric pressure into a theoretical altitude, showing how heat acts like extra elevation. On an afternoon with temperatures reaching 40 degrees Celsius, a sea-level airport can have a density altitude of over 5,000 feet. The airplane behaves as though it is taking off from a mountain runway, even though it is physically at sea level. When high elevation and extreme heat combine, the performance penalties compound. By contrast, cold winter air does the opposite. Freezing temperatures pack air molecules tightly together, giving the engines more thrust and the wings more lift. But during a summer heat wave, that atmospheric advantage disappears. The engine must work harder to produce less, turning a standard departure into a precise calculation of safety margins. The physics of density altitude find their most exacting test at airports constrained by short runways. London City Airport operates with a single runway measuring just 1,508 meters, or roughly 4,900 feet. Under standard conditions, the Avro RJ100 regional jets that serve this urban hub depart with comfortable safety margins. But during a severe heat wave in July 2013, the rising temperature pushed the airport's density altitude to extreme levels. To lift off safely before reaching the end of the concrete, an aircraft must achieve a precise speed to generate lift. As the hot air thinned, the performance of the Avro RJ100 degraded. The aircraft itself remained completely airworthy, mechanically perfect, and legally certified. It was simply too heavy for the physical distance available. This reality left operators with only one variable they could change: weight. To meet the takeoff safety margins required by international aviation law, British Airways City Flyer had to offload nearly 20 passengers from a Geneva-bound flight. Across that single day, 14 flights faced similar operational restrictions. Airlines follow these rules to preserve strict margins of safety. The passenger offload is a direct, calculated consequence of the temperature. When a runway is short, heat transforms a routine departure into a delicate equation where even a few hundred pounds of payload can prevent a safe takeoff. Separate from the physical limits of lift and thrust, there is a third barrier. It might be the most absolute of all. This barrier governs what the aircraft is permitted to do, independent of its physical capability. Every aircraft type operates under a strict regulatory framework. During the design and testing phases, manufacturers and regulators establish a certified maximum operating temperature. This hard limit is written directly into the official airplane flight manual. It is an absolute boundary. If the thermometer at the gate reads even 1 degree above this certified limit, the aircraft cannot turn its engines. Why is this line so unyielding? Because outside this temperature ceiling, there is no flight test data. The manufacturer cannot guarantee how the onboard systems, the tires, or the engines will behave, and regulators will not permit crews to fly into uncharted territory. The flight manual's tested envelope is the final line. When an aircraft sits at the gate in temperatures exceeding its certified envelope, there are no calculations to make, no weight to shed, and no runway long enough to change the outcome. The flight is grounded by law. What happens if a flight crew decides to push the limits anyway? This is where the legal reality of aviation safety catches many off guard. The restriction is not a prediction of immediate physical failure. A modern jet turbine will not spontaneously disintegrate the moment the ambient temperature hits 119 degrees Fahrenheit. Instead, the barrier is a complete vacuum of information. During the certification process, manufacturers test aircraft under extreme conditions, but those tests have practical limits. When Bombardier certified the CRJ900, they mapped its performance characteristics up to 118 degrees Fahrenheit. Beyond that threshold, there are no official charts, no wind tunnel calculations, and no verified safety margins. In commercial aviation, the absence of data is treated as the presence of danger. Without approved performance figures, pilots and dispatchers cannot calculate required takeoff speeds, engine thrust settings, or emergency climb gradients. Operating without this verified engineering data violates federal safety regulations. This is why extreme heat events trigger outright groundings rather than manageable weight restrictions. When there is no data, there is no flight. In airline operations centers, dispatchers and controllers run real-time calculations as temperatures climb. They do not immediately cancel the flight. Instead, they work to save the departure by systematically trimming weight. This operational process follows a strict hierarchy designed to protect both the passengers and the airline's bottom line. First to go is commercial cargo. Freight is the easiest trade-off because it can be rerouted on later flights with minimal penalty. If the aircraft remains too heavy, operations controllers target checked baggage next. Leaving suitcases behind is a logistical headache that guarantees customer complaints at the baggage carousel, but it keeps the cabin full. When cargo and baggage cuts are still insufficient, dispatchers adjust the fuel plan. They can load less fuel to lighten the aircraft, which forces them to schedule an unscheduled refueling stop along the route to the final destination. The absolute last resort is removing passengers. A 70-seat regional jet generates about $14,000 in ticket revenue. Bumping even one traveler means paying immediate compensation, securing hotels, and rebooking. Every pound removed carries an explicit commercial cost. When dispatchers finally make the call to bump passengers, they are not acting out of convenience. They are translating the hard, uncompromising physics of hot air into a costly operational reality. When an aircraft cannot meet its required safety margins in the midday heat, dispatchers face a choice: trim the payload now or wait for the air to cool. This is not a matter of intuition or customer convenience. It is a cold mathematical trade-off played out on performance charts. How does a dispatcher decide? They run the calculations for the projected evening temperatures. If a delay of 3 hours promises a drop of 5 degrees Celsius, that temperature shift might restore just enough AR density to reclaim the lost margins. But this strategy only works if the ambient temperature drops far enough, fast enough. If a high-pressure system keeps the runway sweltering into the night, delaying the flight merely postpones the inevitable offload. The numbers do not bend. A flight may justify a careful delay, but never permission to ignore the charts. This operational reality explains why extreme summer heat rarely leads to dramatic, network-wide cancellations. For the vast majority of aircraft, the daily battle against rising temperatures is quiet and procedural. It is resolved behind the scenes through careful cargo adjustments, minor fuel changes, or a brief wait for the evening breeze. The planes still fly, but only when the arithmetic of the air matches the reality of the runway. What changed? For decades, extreme heat was an occasional regional disruption, but on June 20th, 2017, the problem demanded wider attention. In Phoenix, the temperature hit 119 degrees Fahrenheit, crossing the 118-degree certified limit for Bombardier CRJ regional jets. American Airlines canceled more than 40 flights in a single afternoon, leaving thousands of travelers stranded. Soon, the issue spread to other regions: heat waves. In 2018 and subsequent years forced passenger bumping at airports with short runways, showing the problem extended past a single headline. By the summers of 2024 and 2025, major United States carriers routinely left heavy baggage and passengers behind to meet safety margins. No longer is this a rare curiosity. Peer-reviewed research projects that by mid-century, 10 to 30% of annual flights at major airports will face takeoff weight restrictions. The legal and physical limits have not changed. The atmosphere has. Modern aviation is simply being pushed against those limits far more often. To counteract this shrinking envelope, the aviation industry employs several tactical adjustments. Airports can extend runways, and airlines routinely shift heavy departures to the cooler, early morning or late evening hours. Next-generation aircraft with advanced aerodynamics and higher bypass turbofans also offer improved hot and high performance. Yet none of these measures rewrite the laws of thermodynamics. They merely buy margin. A longer runway provides more room to accelerate, but it cannot restore lost engine thrust. Scheduling mitigations help on ordinary hot days, but fail when a severe heat wave keeps the runway sweltering past midnight. Adaptation is real, but it remains partial. At the terminal gate, a passenger stares out at a perfectly sunny sky, feeling stranded by what looks like an overreaction. In the operations center, a dispatcher reads a non-negotiable performance chart. This is neither crew error nor bad judgment. Both individuals are reacting rationally to the limits of their worlds. The underlying friction is simple. A global flight schedule built for a cooler climate is meeting concrete that keeps getting hotter. Can you blame either of them? The unresolved question is whether industry adaptation will happen fast enough as payload restrictions become a daily reality. Airlines can rewrite their schedules, but physics does not negotiate. Subscribe for more aviation documentaries. Aviation has always operated on margins defined by physics, not convenience. As global temperatures rise, the industry faces an uncompromising line drawn by nature. The hard physical limits of density altitude cannot be negotiated. In a warming world, safety means accepting that sometimes the air itself is simply too thin to support us. Subscribe for more analytical insights into modern aviation.